This is section 7.8, part 2. And in this section, we're going to be looking again at improper integrals, but these are improper for a different reason. Rather than the limits of integration themselves being either positive or negative infinity, we're going to look at integrating functions that have a discontinuity, specifically an infinite discontinuity. Take a look at this first picture. This graph y equals f of x has a vertical asymptote here at a, or an infinite discontinuity. And if I want to integrate it from a to b, I already know there's a problem at a. So, just like we were doing before, we're going to replace the problem spot. We're going to say, instead of listing it directly as a, let's do the integral from c to b, and then just take the limit as c approaches a from the right. We can come in the other way too. If the area that we want is actually to the left of our discontinuity, then we do the limit as c approaches b from the left and approach that way. Okay, in this particular case, then it's the upper limit that's got the problem and the upper limit that we'll replace. We're always replacing the value that's causing trouble, the value that's really the vertical asymptote, where that infinite discontinuity exists. Sometimes the infinite discontinuity may exist in the middle of the integral, like in this last picture. Here, p is where I've got a vertical asymptote. And when that happens, we actually have to split our integral up. We have to go from a to p, and then from p to b. We can't go directly from a to b because we're skipping over that problem spot, that vertical asymptote. All right, let's look at a couple of examples. Again, always remember, it's the problem spot that we're going to replace with a limit. In our first example, I'm looking at the function that I'm trying to integrate, and I'm going to say, where's the problem? Problem is when the denominator is 0. So if e to the x minus 1 is 0, then the 2/3 power would still be 0. That's the problem. That happens if e to the x equals 1, which happens when x equals 0. Okay. So x equals 0 is my problem spot. Now I notice 0 is one of my limits of integration, so that's the one I need to replace with a limit. I'm going to take the limit, and we can call it any letter we want. I'll say as a goes to 0, and I only need to approach from the right. And then I'll say that's the integral from a to natural log 3 of this function. All right, so let's see here. In order to do this integral, it looks like I'm going to need a U-substitution. Let's let u be e to the x minus 1. So du would be e to the x dx, which I have right here. Since I'm substituting, I won't put my limits of integration in right now. Those are values of x, not u. I would have, this would be u, and I'm going to write it to the negative 2/3. And then the e to the x dx is simply du. All right, integrating that's going to give me u to the 1/3. I'm going to put my u back in right now. And dividing by 1/3 would be multiplying by 3. And that then gets evaluated from a to ln 3. All right, so I'd have 3 times. First of all, I have e to the ln 3 minus 1 to the 1/3. And then minus 3 e to the a minus 1 to the 1/3. That would be 3 times. E and ln are inverses, so that's really just 3 minus 1, or 2, to the 1/3, minus 3. If a becomes 0, that's just e to the 0, minus 1, to the 1/3. That's 1 minus 1, or 0, so this whole thing goes to 0. And I just end up with 3 times 2 to the 1/3, or 3 times the cubed root of 2. So this one converged. We got a finite value. All right, let's try the next one. We're integrating really just 1 over x minus 1 to the 1/3 dx. And our problem here is x equals 1. We'll certainly make the denominator 0. Now notice 1 is in the middle of this, not middle exactly, but it's somewhere within the interval. It's not one of the endpoints. So that means I'm going to have to split this up. I'm going to draw a picture of this just to kind of help us visualize what's happening here. Our function was 1 over x minus 1 to the 1/3. And as far as a window is concerned, let's see, I know I'm integrating from 0 to 9. I'm going to go just a bit beyond that. Let's go from -5 to 10, let's say. Scale of 1 is fine. And the y values are going to be fairly small, it looks like. I'm going to go with, let's go -5 to 5 and see what happens. You can see that vertical asymptote at 1, as we were expecting. There's supposed to be a problem at 1, right? And our graph looks like that. The integral went from 0 to 9. So I was really trying to find, let's see if this is 9. I was really trying to find the area in here between 0 and 1, and then again over here from 1 to 9. And of course the question is that going to be finite, or is the fact that there's a vertical asymptote and they're going to make it infinite? So let's see. I'll break this up then and do it as 2 separate integrals. First one's going to go from 0 to 1. And the second one's going to go from 1 to 9. All right, 1 is our problem spot. So I'm going to have to replace the 1 with variables, and they'll have to be separate. In this first one, let's say it's the limit as a goes to 1. And since we're going from 0 to 1, we're approaching the 1 here from the left. Integral from 0 to a, and I'm going to write that as x minus 1 to the -1/3 dx, plus this next one, I'll say the limit is b goes to 1, and in this integral from 1 to 9, notice we'd be approaching the 1 from the right. That'll be from b to 9. And again, I'll just write that as x minus 1 to the -1/3. All right, I'm going to see if we can do sort of a mental U-substitution here. If we let u be x minus 1, du is just going to equal dx, so there's not going to be any correction at all. So I think we can just kind of integrate pretending that this is like a u. So let's see. I would have x minus 1. Adding 1 to the exponent would be positive 2/3. Dividing by 2/3 is the same as multiplying by 3/2. And that goes from 0 to a. My second integral, same deal. We would once again get 3/2, x minus 1 to the 2/3. And this one goes from b to 9. All right, plugging in my limits of integration, I would have 3/2 times a minus 1 to the 2/3, subtract 3/2 times 0 minus 1 to the 2/3, plus, same thing here, we'd have 3/2 times 9 minus 1 to the 2/3, subtract 3/2 times b minus 1 to the 2/3. All right. In this first integral, a is approaching 1. So since this a is going to 1, I'm going to get 1 minus 1, or 0, for that whole first term. And that's going to give me negative 3/2 times negative 1 to the 2/3, which would be 1, right? Yeah, because that'll become a positive 2. Or, excuse me, negative 1 squared is positive 1. Cubed root is still 1. Plus, here, that would be 8 to the 2/3. So I'd have 3/2 times 8 to the 2/3 would be 4. And in this part, as b goes to 1, that's again 1 minus 1, or 0. So this whole term goes to 0. And I end up with negative 3/2 plus 12/2, or 9/2. Once again, I got a convergent integral, so there is a finite area that I'm talking about there. All right. Couple more of these. In example 3, we have the integral from 0 to e of natural log x dx. And let's see here. The problem here is going to be at 0, right? We know the natural log graph has a vertical asymptote on the negative y-axis. Let's see, the natural log of e is 1. So if I were to sketch this, what I'm actually trying to find is this area, which goes down along the y-axis toward negative infinity on the asymptote, and then this one. This will count as negative, that'll count as positive, right? All right, let's see what we can do. The problem again is in the middle. Or excuse me, no it's not. The problem's on the vertical asymptote over here, my fault. The problem's at 0. So we can go ahead and just replace the 0. And we'll rewrite this as the limit as a goes to 0. And let's see, we'd be approaching 0 from the right. Integral from a to e ln x dx. That's an integral that I don't know. It's not actually on our short list, but I bet it's on the big one. It's probably even a basic integral. Yeah, here it is. Number 11. So my integral is x ln x minus x. And that goes from a to e. So I'll get e ln e minus e, subtract a ln a minus a. This part's no problem. This would be ln e is 1. So I've got e minus e, which is 0. Minus this part. This part's more of a problem. So I'm going to go ahead and rewrite this part. Actually, the minus a part's no big deal, right? That part's just 0. But this part's where my problem comes in. A is going to 0, and the natural log of 0 coming in from the right is negative infinity. So what I've got here is an indeterminate form. To evaluate the limit of an indeterminate form, something that would work with L'Hopital's rule would be great. Right now, I don't have anything that quite works for me, so I'm going to have to do a little rewrite on this. We've seen this before. So I have got negative limit as a goes to 0 from the right. And let's go ahead and we'll leave that ln a on the top, but I'm going to move this a to the bottom and write it as an a to the negative first. Now the natural log of 0 is again negative infinity, but 1 over 0 goes to infinity. So infinity over infinity, this is a L'Hopital's rule form. So I'll have negative the limit as a goes to 0 from the right of derivative of the top, 1 over a, derivative of the bottom, minus a to the minus 2, that would be negative 1 over a, and I can bring this up as a times a squared. One of those a's will cancel out. And as this goes to 0, the whole limit becomes 0. So it did converge. And notice that geometrically, what does this tell me? Since I got 0 for the value of the integral, it must be that this area that counts negative and this area that counts positive must be the same. This one just counted negative, that one just counted positive. They canceled themselves out to get 0 for the final limit. All right, last problem. I would like to find the area of the region under this graph on its entire domain. So first of all, I'll notice that clearly I can't have a negative under the radical, so I think x is going to have to be between plus and minus 3 to keep a positive down here. But I can kind of verify that with a quick little graph here. And let's see, I'm going to go negative 5 to 5 for my window, both axes. And there we go. You can see those, the starts of the vertical asymptotes here at 3 and -3. So if I was going to sketch this, I'd have vertical asymptotes at plus and -3. And the graph kind of looks like this in between. Right, stays just above that x-axis. I'm looking for the area under that graph. So it would go up to infinity here near the asymptotes, get squeezed down very small near the origin, and then go back up towards infinity again. All right, we once again want to find out if that's getting squeezed down small enough so this converges or whether it diverges. I'm going to once again use some symmetry here. I'm going to say that it's pretty clear to me that the two sides here are the same. So rather than having to deal with two discontinuities, one at -3 and one at +3, let's go ahead and just do the area on this side, and then we'll double it by symmetry. So I'm going to say my area would equal 2 times, and then I'll just do the integral from 0 to 3 for this function. So the problem is at 3, problem spot at 3. Meaning I can't leave the 3 as a limit of integration. I have to replace it. So we'll have 2 times the limit as, let's say, b goes to 3. And we'll be approaching 3 from the left. Integral from 0 to b of 1 over the square root of 9 minus x squared dx. Now once again, that looks pretty familiar. I think that's one of my integrals. Might even be one of my basic integrals. So I'm going to kind of look over here on my list. And let's see here. It actually looks like this one, doesn't it? The inverse sine. My a is 3, since a squared is 9. So this would be number, I just had it, where'd it go? Here it is, number 14 with an a of 3. It's going to give me the arc sine of x over 3. Like so. All right, so plugging in my limits of integration, I would have the arc sine of b over 3 minus the arc sine of 0 over 3. And let's see, when I plug in the b equals 3, that's just going to give me the arc sine of 1 minus the arc sine of 0. And those are just values that I can plug right into the calculator. Okay. If I just take the inverse sine of 1, notice that looks like a lot like pi over 2, which is exactly what it is, right? The sine of pi over 2 is 1. And the arc sine of 0 sure should be 0, but we can verify that. It is indeed. So 2 times pi halves is going to give me pi. And that brings us to the end of section 7.8.